Hello everyone, welcome to CS30. For this lecture video, we will talk about partial order relations. Recall that in the past lectures, we talked about these properties and also the concept of equivalence relation, which is a relation that is reflexive, symmetric, and transitive. What is interesting about equivalence relation is that it leads to a partitioning of a certain set, and any partitioning of a set also provides an equivalence relation. Let's also recall the property of these operations on the set of real numbers. As can be seen, only equality is an equivalence relation. It's reflexive, symmetric, and transitive. Every number is in its own equivalence class. Let's now talk about another special type of relation that enables us to order elements of a set. As stated in this definition, a relation R defined on a set X is a partial order relation if and only if it is reflexive, antisymmetric, and transitive. So we will then refer to X as a partially ordered set or poset under relation R, and the set and the partial order relation is collectively called a poset. So going back to the property of some operations on real numbers as given here, notice that there are two operations that satisfy the condition of partial order relation. So that's equality and the less than or equal relation. So they are both checked in the reflexive, antisymmetric, and transitive property. In order to visualize the properties of a partial order relation, let's take a look at this diagram. What is this diagram? This is representing the less than or equal relation on numbers 1, 2, and 3. So as can be seen visually, it is reflexive. There's an arrow pointing to the same number. It is also transitive. If X relates to Y and Y relates to Z, then X relates to Z. And why do we say that it's antisymmetric? So recall the requirement for antisymmetry is if X relates to Y and Y relates to X, then X equals Y, right? So what is the contrapositive of this? If X is not equal to Y, then at least one of the following must not hold, right? So in the context of this diagram, we can see that for any two distinct numbers, there is only one arrow connecting them, right? Here, we don't see another arrow from 2 to 1, from 3 to 2, and from 3 to 1. So there is only one direction. Now, it is also important to notice that satisfying symmetry doesn't mean a relation doesn't satisfy antisymmetry, as shown by the equality relation here. If we draw the equality relation on the set containing just numbers 1, 2, and 3, so equality relation will look like this. There's just one arrow pointing to the same number. So why do we say that it is still antisymmetric? Notice here that the only case where X relates to Y and Y relates to X is if both case represents or refers to the same arrow, right? So if X relates to Y, it's this arrow, and Y relates to X is also this arrow. So that is the only case where this will be true, no? And in that case, X is just equal to Y. Let's now revisit the divides relation and define it on the set of positive integers so that we will have this relation. How do we show that R is a partial order relation? The proof idea is to show that R is reflexive, antisymmetric, and transitive. So let's start with reflexivity. So here we need to show that X divides X. X can be rewritten as 1 times X, right? And so X divides X. Next, antisymmetry. Here we need to show that if X divides Y and Y divides X, then X is equal to Y. So let's suppose that X divides Y and Y divides X. So what will that imply? That will imply that Y can be expressed as X times some integer K, and X can be expressed as Y times some integer L. So note that X and Y are positive integers, so K and L must also be positive. Now what do we do next? Our goal is to show that X is equal to Y, right? So we combine these two in one equation by substituting one for the other. So for example, we can substitute what? We can substitute X here using this equation. So that will have Y equals Y times L times K. Now from here, we can divide both sides by Y, so that we'll have 1 equals L times K. Now, the only product of two positive integers that will equal to 1 is 1 times 1. Therefore, L must be 1 and K must be 1. And thus, X is equal to Y. Okay, next, transitivity. So here, if we want to show that if X divides Y and Y divides Z, then X divides Z, right? So let's first assume that X divides Y and Y divides Z. So the consequence is we can write Y as X times some integer K, and Z can be rewritten as Y times some integer L. So what our goal is to show that X divides Z, right? So we must show that Z can be expressed in terms of X times some positive, X times some integer. So how do we do that? Again, we can combine these equations by substituting Y with this value here, right? So that we'll have Z is equal to X times K times L. So now we have Z expressed in terms of X times this. K is an integer, L is an integer, and integers are closed under the multiplication operation, and therefore this will result to one integer, and this shows that X divides Z. Okay, so now that we are able to show that R is a partial order relation, we can say that collectively the set of positive integers with the divides relation is a poset. As an exercise, consider the inclusion relation that relates sets. So, question, is inclusion a partial order relation? The short answer to this is yes. So, you just need to prove that all the criteria for partial order relation is satisfied by this relation. Given a partial order relation, R, we say that two elements are comparable if and only if they are related with respect to R. A partial order relation R on a set X is called a total order relation or a linear order relation if every pair of element is comparable. We then say X is a totally ordered set under R. So what is the saying? Every pair of element is comparable. This is saying, we can think of this as every element is ordered or can be arranged under relation R. And so we say that we have a total order. So if every element is ordered, we can determine who comes before and who comes after an element based on the relation, and thus we can line them up. Later, we will have a better visualization on this, but consider this example for now. So this is a visualization of the less than or equal relation on numbers 1 to 4. So 1 is less than 2, less than or equal. 1 is less than or equal to 2, 2 is less than or equal to 3, and so on. So, as can be observed here, we always have one arrow for every pair of element. So, in general, the less than or equal relation over the set of real numbers is a total order relation. An example of a partial order relation that is not a total order relation is this inclusion that is relating subsets of a certain set. So why do we say that this is not a total order relation? So we must be able to show one case, one scenario where we have two subsets that are incomparable. So what could that be? So one case is when the elements of the smaller subset is not all present in the larger subset. So an example is, let's say we have a subset AB and then another set containing just C. So these two subsets will then be incomparable. Visually, we have this. We have S composed of elements A, B, and C. So given here is a visualization of the inclusion relation on the subsets of S. So notice that we have some pairs with no connection. So for example, the one we mentioned earlier, A versus BC. So there's no arrow from A to BC or BC to A. And also, those that are in the same level, they don't have a connection with one another. For the next definition of a relation, we have to first introduce the concept of a string. For that, we start with a set of symbols, which we will call alphabet. Let's denote that with this symbol, sigma. A finite word or string over sigma is a sequence of symbols, where each symbol is from sigma. The length of a string is denoted by this expression. It represents the number of symbols of that string. So note that the length can be a positive number, but it can also be 0. There is a special term we use to refer to a string of length 0. We call it an empty string, and we denote it by this symbol, which we will call epsilon. We can observe from this that this is inspired by how we use alphabet and words in the English language. right? The concept of alphabet, of word. Although here we are defining it in mathematical terms, and as a result, it can be generalized. So an alphabet is not just limited to 26 characters. It can be shorter, it can be more than 26. For example, here we have an alphabet that is only composed of 3 characters, A, B, and C. So the set of all finite strings over this alphabet is as follows. So you have your empty string, length 0, A, B, C. So these are your strings of length 1, AA, AB, AC, BA, BB, BC, and so on. So all these will be your strings of length 2, and so on. Notice that the way I listed the strings in this set follows a pattern, right? So the 0 length first, and then the strings of length 1, the strings of length 2, and so on. And also, within each group, based on length, notice that the way I listed the strings actually uses the way the symbols are listed in this alphabet. So, for example, for the strings of length 1, I listed A first, and then B, and then C. And then for those of length 2, I included first those strings that start with letter A, and then followed by those strings starting with letter B, and then strings starting with letter C. And I even follow the listing of symbols in the alphabet for how I'm going to order AA, AB, and AC, right? So the point is, I am ordering the strings based on an ordering of the symbols. Now, there are other ways to list down strings. One popular way of listing is a listing that follows how strings or words are listed in a dictionary. So, for example, suppose I only have these strings. Let's exclude the empty string first, because you don't see an empty string in a dictionary, right? So suppose I only have these strings. So how will they be ordered? How will they be found in the dictionary? Which string will be seen first? So you will first encounter A, right? And then will you encounter B next? No, right? Because in the dictionary, we list first all those words that starts with A. So the next word or string that will be encountered will be AA instead of B, right? And then AAA, right? And then AB, AC, B, BA, BB, BC, C, CA, CB, CC. So I will leave it to you to verify that this will be the ordering of strings considering how it is ordered in a dictionary. Okay? So there's actually a particular name for this type of ordering. Specifically, it's called lexicographic ordering. Lexicographical ordering can be defined provided we have an alphabet, the set of all finite strings over the alphabet, and a partial order relation on the alphabet. We will use this notation to represent lexicographical ordering. We can observe that this is similar to the less than or equal relation in numbers. We will thus read this just as in the less than or equal relation, although we will apply this on strings. Okay, the lexicographical ordering relation, denoted by this symbol, is a relation over S, the set of all finite strings over sigma, defined as follows. So we have three items here. First, so let's take some time to read it. So we have two strings. Let's call this string X and string Y. String X has length M, string Y has length N. If M is less than or equal to N, and both strings have the same symbols in their first M positions. In other words, we can think of string X as a substring of string Y. Then, we will say that string X is less than or equal to string Y. Next, given two strings, string X and string Y, again, one string X has length M, string Y has length N. If both strings have the same symbols in their first k-1 positions, but then differs on the kth position, and the kth symbol in string X comes first before the kth symbol in string Y, as expressed by this expression. Xk relates to Yk in the partial order relation R. Then we will say that string X is less than or equal to string Y. Finally, this is to consider the empty string. So as given here, the empty string is always less than or equal to any string in the set of all finite strings. Okay, so let's apply that on some example. So if we consider our alphabet sigma to be the set of, let's say, lowercase English letters, so that's your sigma, then you can define S, right? And then your partial ordering relation will be the relation imposed by the position of letters in the Roman alphabet. Then, in the lexicographical ordering that follows this definition, we know that the word play is less than or equal to playhouse. So play comes before playhouse. Why? Because of condition 1, right? Item 1. The first 4 letters are the same, but the second string is longer. In other words, play is a substring of playhouse. And so we say that play comes before playhouse. Next, playhouse is less than or equal to playmate. Since these strings differ in the fifth position and H comes before M in the Roman alphabet. So this is because of item number 2, right? So in this case, playhouse and playmate have the same symbols for the first 4. So they both have play. But in the fifth position, so this is your K. This is your K, where they now differ on the fifth position. One has H, one has M, and H comes before M in the Roman alphabet. And so we say that playhouse comes before playmate. We end this lesson by introducing the concept of a hash diagram. A hash diagram is a visual representation of a partial order ring. It leaves out edges that must be present because of the reflexive and transitive properties. So how do we construct a hash diagram given a finite OSET? So as given here, we have to perform these 3 steps. We will start with the original diagram we introduced earlier. So note here that the term vertex is used to represent the visual representation of an element in X. And the term edge is used to represent the connection between 2 vertices. Okay, so let's start with the first step. Remove loops that follow this. So these are arrows that originates and points to the same element. And these are present due to the reflexive property. So we already know that partial order relations are reflexive, right? So these need not be represented visually. And so they are removed in a hash diagram. Next, remove all edges that are present due to transitive property. So remove all edges xy for which there is an element z such that x relates to z and z relates to y. So why can we remove this if we already know that this and this are in the visualization? Because with transitivity, we know that this can be inferred from this too. Next, arrange each edge so that its initial vertex is below the terminal vertex. Replace the arrows by lines because all edges point upwards towards their terminal vertex. So for each edge, we want to arrange them such that the origin of the arrow is below the destination of the arrow. Okay, so that the direction is clear. We can then replace the arrows by lines because all edges point upwards towards their terminal vertex. Okay, so let's apply that on the example we had earlier. Recall that this is a visualization of the less than or equal relation for numbers 1, 2, 3, and 4. So the first step is to remove self-loops, right? These arrows that are due to the reflexive property. So we remove them. Next is we remove those that are present due to the transitive property. So what are those? This relates to this relates to this, so we can remove this. This relates to this, and this relates to this, so we can remove this. This relates to this, and this relates to this, so we can remove this. Okay? And so we'll have this. Now, what I did earlier is to already arrange them such that the initial vertex is below the terminal vertex, right? For this arrow, and for this arrow. So this part is already uh, fixed or okay for this representation. So we only need to do this part, that is replace the arrows by lines because all edges point upwards toward their terminal vertex. So we only need to replace this by this, and then we're done. So this is the hash diagram of the less than or equal relation on numbers 1, 2, 3, and 4. That concludes this lecture video. Thank you very much for listening.